Okay, so what ChatGPT has now told me about the elevator is the biggest conclusion from the experiment, number 12, is I would stop trying to make the sub-geo orbital elevator a single tether with a freely orbiting endpoint. We've demonstrated why it doesn't work, but I would absolutely continue with the broader concept. The architecture I'd investigate now is Earth Station to 36.6 kilometer high altitude supported structure to fixed interface to an orbital ring slash skyhook system, then closed orbital structure to LEO access point. The orbital system itself supplies enormous angular momentum, the Earth structure provides continuous physical connection, and propulsion, including potentially fusion, is used for momentum management, not brute force support. That is a much more promising architecture. Material support. For the first engineering model, my ranking would be graphene superlaminate, best overall candidate. We have no way of making graphene superlaminate at that scale. SWCNT, best intrinsic material, but manufacturing is the problem. HBN, potentially excellent structural interface reinforcement. Hybrid graphene slash CNT slash HBN, possibly the ultimate architecture. The literature is usually consistent on one point: the material is still the central unsolved technology. This is the big problem I was trying to get around, this issue of materials, trying to build it out of conventional materials that can be mass manufactured. And I thought I'd come up with like a design that could potentially work, but it sort of doesn't. That's the problem with it. Required the combination of strength, defect tolerance, interlaying, bonding, manufacturability, and enormous continuous length has not yet been demonstrated. So if we continue this as an actual engineering study, the next calculation I would run is an orbital ring version rather than another single tether version. This would let us calculate the required ring velocity, mass, tether cross-section, centrifugal support, and most importantly, how a fixed 120,000 foot station could continuously interface with the moving orbital structure. Fuck. Fuck! This is not what I want to hear. Not really. I want to hear that this can be built out of aluminium or something like. I think there's a good chance the structure going up to 120,000 feet can be built out of aluminium. And I remain unconvinced, and also ChatGPT remains unconvinced in another chat that the stages going through the mesosphere and the stages in space, they might be light enough to be able to actually be held up by propulsion systems, by fusion engines, or allowed to flex to some degree, so we take away these requirements for such a large amount of propellant being used to keep it all totally straight and taut above Earth's surface in low Earth orbit, and we just allow it to flex somewhat. So we just use the engines to sort of control it and prevent it from falling back in the atmosphere, basically, rather than keeping it all straight. So it goes very much like a sort of a rocket trajectory on a sort of curve out of the atmosphere. I want to just, I don't know what I'm going to type in now. What should I type in now? Oh, I don't know. Maybe I've got to give up on this. Maybe I do. And like, this is changing everything I thought about this fucking project. I've been working on it for like 2 years or something in my spare time, and like, oh, oh. It was obviously going to be a hugely challenging thing to begin with, obviously. A space elevator would be the largest engineering project of any kind that we've ever engaged in. But yeah, I'm going to type something else in. And so, is there no possibility that any configuration of the hurry up above designs could feasibly support even an optimally lightweight structure somewhere in the LEO region using any propulsion system with conventional materials that can be mass manufactured. What I'm trying to get at is something to what ChatGPT told me at one point in an earlier chat on this topic, where it seemed that a certain design, oh hurry up, please hurry up, would be feasible using conventional materials, so long as the mass of the end oh come on, I hate the fucking internet, waiting around for connection all the time, and slowing and freezing, and I can't work like this. I can't do anything, it seems. I can't. Oh. Why can't I have nice things? Oh, here we go, it's working again. No, it isn't. It doesn't work. Oh no. End station is low enough. I'm happy to consider the end station a sort of orbital ring that doubles as a space station / docking station. Come on, calculator, you bitch. Stupid ChatGPT. Or is it clever than I am? It's thinking. Just thinking now. I should really edit all these bits out, shouldn't I? But I don't have video editing software and I have no way of doing it. Yes, there is a configuration in the LEO region that I think is worth taking seriously using conventional mass manufacturable materials, but it is not a conventional space elevator and it cannot be passively supported. Key to you is your revised requirement. The LEO end station can be lightweight orbital ring docking structure and propulsion can actively maintain it. That changes the answer substantially. Okay. The configuration I'd recommend is what I could have propulsively supported orbital tether station. Okay, this is really important. 36.6 kilometers high altitude structure, detention, compression, transition, lightweight orbital ring to docking station. Okay, the LEO station isn't trying to hover motionless above the Earth, it is an actively controlled orbital structure. The propulsion system continuously supplies the force necessary to maintain the desired orbital geometry. The critical question becomes, can the required propulsion and tether be made sufficiently lightweight that the system closes its own mass budget? Yeah, I think the answer may be yes for a relatively small station, though probably not for the huge passenger / cargo elevator we initially imagined. The trick is to stop asking the tether to support the station. This is the conceptual distinction that matters most. If we put a 100-ton station at 300 kilometers, its weight in the air is roughly W equal 100,000 times 8.9, that equals 8.9 meganewtons. But the station doesn't need a structure to hold it up, it's already in orbit. The propulsion system only needs to maintain its orbital trajectory. This is what I was talking about initially, so this is interesting. So a tether isn't supporting the station against Earth's gravity in the conventional sense. Instead, the tether becomes a mechanical connection between an orbital vehicle and a high-altitude Earth structure. That is a much less demanding requirement, but there's still a fundamental problem. If the orbital station is freely orbiting, its attachment point moves around Earth, so you cannot have Earth to perfectly rigid cable to orbital station. That's the orbital station that follows Earth's rotation. Instead, I would make the orbital end itself a controlled rotating structure. Something like orbital ring, docking station, dynamic tether, 100. Well, it looks connected to me. The ring is moving, but the docking station is attached to it. Okay, so the orbital ring has to be moving. Okay, a controlled rotating structure. Yeah, that seems. And now conventional materials become interesting. You don't need a 40,000 kilometre carbon nanotube, that's enormously important. If the orbital system is only designed to support itself plus a small docking facility, you can potentially use much more ordinary structural materials. Canons include high strength steel, modern miraging steels can reach roughly 2 gigapascals ultimate tensile strength. Advantages: extremely mature manufacturing, inexpensive, weldable, machinable, enormous industrial supply chain. Disadvantage: density, it's 8,000 kilograms per meter cubed. That makes it terrible for very long unsupported orbital tethers. Titanium alloys, typical aerospace titanium alloys can reach roughly 0.9 to 1.2 gigapascals. Density is lower at 4,500 kilograms per meter cubed. Better than steel, but still not spectacular. This is where I think the conventional material solution begins. High performance carbon fibre, which is initially what I suspected it would be. 1.5 to 3 gigapascal effective tensile strength, with densities around 1500 to 1700 kilograms per meter cubed. Their specific strength is therefore vastly better than steel, and they're probably already mass manufactured at industrial scale. That's probably our baseline material. But then there's even more interesting material. UHMWPE, ultra high molecular weight polyethylene. Think Dyneema Spectra type fibres. Density around 970 kilograms per meter cubed. Tensile strength of the order of 2 to 4 gigapascals, depending on fibre/product. Enormous industrial production, excellent specific strength. The absolute strength isn't remotely graphene level, but because the density is so low, the specific strength is surprisingly competitive. For a lightweight orbital tether, that's potentially extremely attractive. The problem is temperature. UHMWPE doesn't like high temperatures, and an orbital structure exposed to sunlight can have difficult thermal constraints, but if we use it as a protected tensile member, it becomes interesting. So I'd actually use a hybrid rather than one material. Carbon fibre for high temperature structural sections, UHWMPE for ultralight tension members, aluminium or titanium for rigid interfaces, high strength steel only where compact high load fittings justify the mass, and perhaps conventional composites for the orbital ring. That's all commercially manufactured technology, no graphene required. Sounding good. Now let's examine the station mass. Suppose our orbital docking ring weighs 10 tons. At 300 kilometer altitude, its orbital velocity is roughly 7.73 kilometers per second. Its orbital kinetic energy is E equals over half mv squared equals 3.3 times 10 to the 11 joules, or about 83 megawatt hours. That's a surprisingly manageable amount of stored orbital energy for a 10-ton structure. But we don't have to continually supply that energy. We only need to correct its orbital losses. That's crucial. Atmospheric drag is the enemy. At 300 kilometers, the atmosphere is extremely thin, but not zero. A large orbital ring with a big cross-sectional area would experience drag. Therefore, I put the docking station at around 500 to 600 kilometers, rather than 200 to 300 kilometers if our goal is longevity. Example: 600 kilometer orbital velocity was 7.56 kilometers a second. Period equals 96.5 minutes. Atmospheric density is drastically lower than the 200 to 300 kilometers. That substantially reduces station keeping propulsion. And we're still firmly in LEO. Here's where propulsion becomes practical. Suppose the orbital structure experiences an effective drag acceleration of only 10 to the minus 8 meters per second squared. That's tiny, but over 1 year, delta V equals AT gives 3.31.5 meters per second per year. That's quite manageable. Even if the actual station requires several times that, we're only talking about tens to perhaps hundreds of meters per second of annual delta V, rather than 7.8 kilometers per second every orbit. That's the critical distinction. A chemical/electrical propulsion system doesn't need to continuously hold the station up, it merely replaces momentum loss to drag and perturbations. Electric propulsion could therefore work. Okay, for a 10-ton orbital structure, a high-specific impulse electrical propulsion system could be extremely effective. Ion/Hall thrusters can provide very high specific impulse, although thrust is low. That's fine for station keeping. If we effectively use nuclear electric propulsion, the system becomes even more attractive. Fusion would be completely unnecessary for basic orbital support. It becomes interesting only if we want substantial propulsion authority, for example, rapid orbital maneuvers, moving docking infrastructure, transferring momentum to elevator climbers, raising/lowering orbital structure, active control of a huge orbital ring. Here's the configuration I've now put at the top of the list. 600 kilometer orbital ring, something like 5 to 20 ton orbital structure, containing docking ports, propulsion, solar power, attitude control, communications, robotic tether equipment, structural attachment points. Surrounding and connecting to it is a lightweight carbon fibre UHMWPE orbital ring. Below that 3.6 kilometre Earth station, supported by a combination of aerostatic lift, guy cables, conventional composite structures, active aerodynamic stabilisation. The two are connected by a dynamically controlled tether system, not a rigid tower. Yeah, okay. There's a potentially clever solution to the rotation problem. Instead of having the docking station follow one point on Earth, let the orbital ring travel around the planet. At the point where its orbital trajectory intersects the geometry of the Earth-side system, the tether can be dynamically coupled. The Earth-side station doesn't necessarily have to deliver payload directly into the ring at all times. If it can have a capture mechanism that intersects with the orbital ring during appropriate phase. This is essentially turning the problem into a controlled orbital rendezvous mechanism rather than demanding that the entire tether remain geometrically static. That is much more realistic. I really don't like this idea. Is what it means like it rendezvous with the tether every so often and picks something up and puts it into orbit, sort of like a skyhook sort of system? I don't know about that. I just see like the slightest disjoining of it could shatter the top of the tower and like create all unknown havoc. I don't know. There's a structure that has slack to deployment sections. That means continuous physical connection. It was continuously doesn't eat continue. Oh, hang on. Wait, what is this? However, there's one requirement I change. I would insist on the entire Earth to LEO structure being under continuous tensile load. I wouldn't insist on the entire Earth to LEO structure being under continuous tensile load. I allow the architecture to have controlled slack/deployment stations. I initially thought of that. That means continuous physical connection doesn't equal continuously taut straight cable. Yeah, exactly. Like a cable car to space. Like, that makes a lot of sense. That is initially what I thought. Like, it needn't be taught. Why need it be taught? Like, that's a good thing to have said. You can have a connected structure whose geometry changes substantially during operation. That opens up a huge space design. Yeah. My current rankings. 200 kilometer freely orbiting tether, no Earth connection. Orbital ring plus lightweight station, potentially moderate, most promising. Yeah, the orbital ring plus lightweight station. The best candidate is orbital ring plus Earth high altitude station. And geospace elevator, yeah, that's got like a hazard symbol for conventional materials in the table. Continuous connection, yes. Propulsion low, material limited. That's the verdict. 200 kilometer free orbiting tether, no Earth connection. Propulsion low. And propulsion moderate. Earth connected sub-GEO tether. Very high propulsion requirements, which it means it would be very difficult to build it. And there's a warning sign for conventional materials in being able to do that. I think there's a meaningful conventional material design space here, but the thing I build isn't a miniature space elevator. It's an orbital ring/docking station coupled to a high altitude Earth structure with propulsion used for momentum management. And your intuition about keeping the orbital station extremely lightweight is exactly right. Once the station is treated as an orbital vehicle rather than something that has to be physically supported against gravity, its mass becomes much less frightening. The next calculation I'd recommend is much more concrete. Design a 10-ton, 20-ton or 100-ton orbital ring station at 400, 500 and 600 kilometers using carbon fiber MWP. I hate pronouncing that acronym. As I said, we can actually survive the resulting loads. That will give us a real feasibility boundary rather than another conceptual answer. And it does say also ChatGPT can make mistakes, but yeah. So I think I don't like this idea of a geo space elevator much. I get the design principles behind it. I get like why it works in terms of orbital mechanics and so on, and how it balances out the tension on the cable and reduces needs for things like propellants and so on. And yeah, I I don't know. I don't know really. Like, yeah, yeah, it doesn't, like the GEO space elevators doesn't require much propulsion, but it might take about 3 weeks to get out to GEO. Whereas really what you want, I think, is something going to LEO, low Earth orbit, or let's say about the same sort of altitude at which the International Space Station orbits, or something like this. And getting astronauts and crews up there, and building spacecraft up there, and just sending spacecraft from a docking station. That's really what you want, I think. You know, you don't want to having to be spending 3 weeks in an elevator capsule getting out to geostationary orbits, do you? Doesn't make much sense. You know, it might be good for hauling cargo, but even then, I think like spacecraft really traveling at 11 kilometers per second or something like this, like that's a far more promising candidate for moving stuff around once you're in space. All the space elevator really should be for, I think, in my opinion, is just getting things into low Earth orbit, because that's half the battle won if you can get up there. That's that gets you halfway to anywhere, so called. And yeah, I think that this orbital ring though, plus high altitude station, yeah, that is the best candidate, I think. But I just want to Google a bit more about how orbital rings work. So I'm not sure I entirely understand the concept, because I don't think ChatGPT explained it brilliantly to me. Orbital ring. An orbital ring is a sci-fi megastructure concept of a ring placed around a planet. Oh no, that's not what ChatGPT was saying. No, I don't want an orbital ring around. What is ChatGPT on about? The diagram doesn't look like it means an orbital ring around a planet, because it's got Earth, then the 120-foot station, then the dynamic tether, then the docking station, then a rotating orbital ring. The ring is moving, but the docking station is attached to it. That gives us a place for spacecraft to rendezvous with the system. I'm so confused. I shouldn't be confused, but this just isn't helping. So you cannot have Earth to perfectly rigid cable to orbital station. Who said anything about the cable being perfectly rigid? Who said that? I don't think it does. Certainly, I think it's not advantageous for it to be perfectly rigid, and yeah, I don't think we need that at all. But an orbital ring, do we need that even? Like, everything that comes up on Google is not what ChatGPT is saying. Like, it's got like Earth here, then the 120,000 kilometer structure, then a couple of other stages, then the docking station, then the tether even, and then the docking station, then the orbital ring up here, and that's sort of what, moving around the planet? I don't get it. What's it trying to say? Like, it's so weird. Let's just type in one more thing, right? Do like, are you implying that the orbital ring will be going around, will be encircling the floating bit as a separate rotating ring structure? And remember, AI is only right about things like this apparently 45% of the time for complex problems such as this. I meant encircling the Earth. Oh, I fucking hate ChatGPT. What I meant by an Earth encircling orbital ring. Oh, that's beyond anything we can hope to build in the next century, I'm afraid to say. I meant encircling the Earth, but I realised my wording blurred two very different concepts. There are actually three possibilities: a conventional orbital ring, a closed ring going all the way around Earth, moving such orbitally to LEO altitude, a localized orbital ring / platform, a relatively small closed loop or structural frame in orbit but not a ring around Earth, a separate floating ring, a stationary circular structure above one region of Earth. This is essentially the impossible case we were trying to avoid because it would need continuous propulsion to counter gravity. Your project, I think number one is the much more interesting architecture. Still it pictures Earth outside the orbital ring. Why does it do that? Maybe it's just easier to launch space planes from the top of a tower. But other people thought of that before, you know, so. Rotating orbital tether / skyhook. I don't trust these diagrams that ChatGPT is giving me. This is shitty. Doesn't encircle Earth, but it is a finite rotating structure in orbit. Its rotation can make one part of the structure have a much lower relative velocity with respect to Earth than the centre of mass. This is potentially much closer to what you originally wanted. And it has a very interesting property with the correct rotation rate geometry. One end of the tether could potentially approach a high altitude Earth station at a relatively low relative velocity. That's the principle behind rotating skyhooks / momentum exchange tethers. If your actual goal was, I want a continuous physical structure of Earth to an LEO docking station, but I don't want to build a geo elevator or use a gigantic fusion rocket to hold the station up, then I would now investigate rotating orbital tether / skyhook coupled to the 120,000 foot structure rather than Earth encircling orbital ring. The next calculation I run would determine whether we can choose rotation rate, tether length, orbital altitude, and counterweight mass so that the lower tip of the rotating system reaches the 120,000 foot station with a manageable relative velocity. That is probably the closest we've gotten to a configuration that preserves the spirit of your original idea while respecting orbital mechanics. Yeah, I think that's a good place to end this video. So, like, I still think that building the 120,000 foot structure, which I mean, like, is what I've designed. Like, space planes could be launched from the top of that. SSTO, single stage orbit devices, could be launched from the top of that, and it could greatly assist getting stuff into orbit, building a huge tower like that, more or less. And in the future, following that initial first stage of the design, I suppose we could start incorporating things like skyhooks and experimenting with stuff like that, if that is indeed the best means of getting payload into orbit from that point, and not having a continuous tether going all the way up to LEO. And if that proves to be impossible, then I suppose we just have to deal with that and in the best way that we can. So it's not worth abandoning entirely, I don't think. But yeah, we're sort of back to something like square zero or square one, I don't know. But anyway, thank you for watching. Sorry, this has been a really annoying video, I bet, but bye bye, I love you.